Section 7.2, Kubernetes Deployments for Spring Boot. This section will walk you through the main Kubernetes objects you'll be working with as a developer and the vocabulary necessary to communicate efficiently with a platform team and deploy your applications to a cluster. You have already gone through the containerization of a Spring Boot application. A Spring Boot application on Kubernetes is still packaged as a container, but it runs in a pod controlled by a deployment object. Pods and deployments are core concepts you need to understand when working with Kubernetes. Let's start by looking at some of their main characteristics, after which you'll practice declaring and creating Kubernetes resources to deploy the catalog service application. Section 7.2.1, From Containers to Pods. As we discussed in the previous section, pods are the smallest deployable units in Kubernetes. When moving from Docker to Kubernetes, we switch from managing containers to managing pods. A pod is the smallest Kubernetes object, and it represents a set of running containers in a cluster. It's usually set up to run a single primary container, your application, but it can also run optional helper containers with additional features like logging, monitoring, or security. See this link. A pod is usually comprised of one container, the application instance. When that happens, it's not much different from working with containers directly. However, there are some scenarios where your application container needs to be deployed together with some helper containers that perhaps perform initialization tasks required by the application or add extra functionality such as logging. For example, Linkerd, a service mesh, adds its own container, a sidecar, to pods to perform operations such as intercepting HTTP traffic and encrypting it to guarantee secure communication between all pods via MTLS, Mutual Transport Layer Security. Figure 7.3 illustrates single container and multi-container pods.
Figure 7.3. Pods are the smallest deployable units in Kubernetes. They run at least one primary container, the application, and might run optional helper containers for additional features like logging, monitoring, or security.
In this book, you'll work with single container pods, where the container is the application. Compared to containers, pods allow you to manage related containers as a single entity. But that's not enough. Directly creating and managing pods would not be much different than working with plain Docker containers. We need something at a higher level of abstraction to define how we want to deploy and scale our applications. That's where the deployment objects come into play. Section 7.2.2, Controlling Pods with Deployments. How can you scale an application to have 5 replicas running? How can you ensure there are always 5 replicas up and running even when failures occur? How can you deploy a new version of the application without downtime? With deployments. A deployment is an object that manages the lifecycle of a stateless, replicated application. Each replica is represented by a pod. The replicas are distributed among the nodes of a cluster for better resilience. See this link. In Docker, you manage your application instances directly by creating and removing containers. In Kubernetes, you don't manage pods. You let a deployment do that for you. Deployment objects have several important and valuable characteristics. You can use them to deploy your applications, roll out upgrades without downtime, roll back to a previous version in case of errors, and pause and resume upgrades. Deployments also let you manage replication. They make use of an object named replica set to ensure there's always the desired number of pods up and running in your cluster. If one of them crashes, a new one is created automatically to replace it. Furthermore, replicas are deployed across different nodes in your cluster to ensure even higher availability if one node crashes. Figure 7.4 shows the relationship between containers, pods, replica sets, and deployments.
Figure 7.4. A deployment manages replicated applications with replica sets and pods in your cluster. A replica set ensures the desired number of pods is always up and running. A pod runs a containerized application.
Deployments provide a convenient abstraction for us to declare what we want to achieve, the desired state, and we can let Kubernetes make it happen. You don't need to worry about how to achieve a specific result. Unlike imperative tools such as Ansible or Puppet, you can just tell Kubernetes what you want, and the orchestrator will figure out how to achieve the desired result and keep it consistent. That's what we call declarative configuration. Kubernetes uses controllers that watch the system and compare the desired state with the actual state. When there is any difference between the two, it acts to make them match again. Deployments and replica sets are controller objects, handling rollout, replication, and self-healing. For example, suppose you declare that you want 3 replicas of your Spring Boot application deployed. If one crashes, the associated replica set notices it and creates a new pod to align the actual state with the desired one. After packaging a Spring Boot application as an OCI image, all you need to do to run it in a Kubernetes cluster is define a deployment object. You'll learn how in the next section. Section 7.2.3, Creating a Deployment for a Spring Boot Application. There are a few options for creating and managing Kubernetes objects in a cluster. In Chapter 2, we use the kubectl client directly, but that approach lacks version control and reproducibility. It's the same reason why we prefer Docker Compose over the Docker CLI. In Kubernetes, the recommended approach is to describe an object's desired state in a manifest file, typically specified in YAML format. We use declarative configuration. We declare what we want instead of how to achieve it. In Chapter 2, we imperatively used kubectl to create and delete objects, but when we work with manifests, we apply them to the cluster. Then Kubernetes will automatically reconcile the actual state in the cluster with the desired state in the manifest. A Kubernetes manifest usually comprises 4 main sections, as shown in Figure 7.5. API version defines the versioned schema of the specific object representation. Core resources such as pods or services follow a version schema composed of only a version number, such as v1. Other resources like deployments or replica set follow a versioned schema consisting of a group and a version number, for example, apps/v1. If in doubt about which version to use, you can refer to the Kubernetes documentation, see this link, or use the kubectl explain object_name command to get more information about the object, including the API version to use. Kind is the type of Kubernetes object you want to create, such as pod, replica set, deployment, or service. You can use the kubectl API-resources command to list all the objects supported by the cluster. Metadata provides details about the object you want to create, including the name and a set of labels, key-value pairs, used for categorization. For example, you can instruct Kubernetes to replicate all the objects with a specific label attached. Spec is a section specific to each object type and is used to declare the desired configuration.
Figure 7.5. A Kubernetes manifest is typically composed of 4 main sections: API version, kind, metadata, and spec.
Now that you're familiar with the main sections of a Kubernetes manifest, let's define one for a deployment object that will run a Spring Boot application. Defining a deployment manifest with YAML. There are different strategies for organizing Kubernetes manifests. For the catalog service application, create a K8s folder in the project root, catalog service. We will use it to store the manifests for the application. Note: if you haven't followed along with the examples implemented in the previous chapters, you can refer to the repository accompanying the book, see this link, and use the project in Chapter 07/07 begin/catalog service as a starting point. Let's start by creating a deployment.yml file inside the catalog-service/Kates folder. As you saw in Figure 7.5, the first sections you need to include are API version, kind, and metadata.
Listing 7.1. Initializing a deployment manifest for catalog service.
Note: the Kubernetes API can change over time. Make sure you always use the API supported by the version of Kubernetes you're running. If you have followed along so far, you shouldn't have this problem. But if it happens, kubectl will return a very descriptive error message telling you exactly what's wrong and how to fix it. You can also use the kubectl explain object_name command to check the API version supported by your Kubernetes installation for a given object. The spec section of a deployment manifest contains a selector part to define a strategy for identifying which objects should be scaled by a replica set, more on this later, and a template part describing the specifications for creating the desired pod and containers.
Listing 7.2. The desired state for the catalog service deployment.
The containers part should look familiar, since it resembles how you defined containers in the services section of a Docker Compose file. Like you did with Docker, you can use an environment variable to define the URL for the PostgreSQL instance the application should use. The hostname part of the URL, Polar Postgres, is the name of the service object that was used to expose the database and was created previously from the Kubernetes Platform Development folder. You'll learn more about services later in the chapter. For now, it's enough to know that Polar Postgres is the name through which other objects in the cluster can communicate with the PostgreSQL instance. In a production scenario, the image would be fetched from a container registry. During development, it's more convenient to work with local images. Let's build one for catalog service as you learned in the previous chapter. Open a terminal window, navigate to the catalog service root folder, catalog service, and build a new container image as follows.
See this code?
Tip: if you're working on ARM64 machines, such as Apple Silicon computers, you can add this argument to the previous command to use an experimental version of Paquito build packs with ARM64 support. Be aware that it's experimental and not ready for production. For more information, you can refer to the documentation on GitHub. See this link. Without this workaround, until official support is added, see this link, you can still use build packs to build containers and run them via Docker Desktop on Apple Silicon computers, but the build process and application startup phase will be slower than usual. By default, Minikube doesn't have access to your local container images, so it will not find the image you have just built for catalog service. But don't worry, you can manually import it into your local cluster.
See this code?
Note: YAML is an expressive language, but it can make your coding experience quite bad due to its constraints about spaces, or perhaps the lack of support from your editor. When a kubectl command involving a YAML file fails, verify that spaces and indentation are used correctly. For Kubernetes, you can install a plugin in your editor to support you while writing YAML manifests, ensuring that you always use the correct syntax, spaces, and indentation. You can find a few plugin options in the readme.md file in the repository accompanying this book. See this link. Now that you have a deployment manifest, let's move on and see how to apply it to your local Kubernetes cluster. Creating a deployment object from a manifest. You can apply Kubernetes manifests to a cluster using the kubectl client. Open a terminal window, navigate to your catalog service root folder, catalog service, and run the following command.
See this code?
The command is processed by the Kubernetes control plane, which will create and maintain all the related objects in the cluster. You can verify which objects have been created with the following command.
See this code?
Since you use labels consistently in your deployment manifest, you can use the label app equals catalog service to fetch all the Kubernetes objects related to the catalog service deployment. As you can see, the declaration in deployment.yml resulted in the creation of a deployment, a replica set, and a pod. To verify that catalog service started up correctly, you can check the logs from its deployment as follows.
See this code?
Note: you can monitor whether pods have been created successfully by inspecting the status column when you run kubectl get pods. Should a pod fail to be deployed, check that column. Common error statuses are error image pull or image pull back off. They happen when Kubernetes can't pull the image used by the pod from the configured container registry. We're currently working with local images, so make sure you built and loaded a catalog service container image into Minikube. You can use the kubectl describe pod_name command to get more information about the error and kubectl logs pod_name to get the application logs from a specific pod instance. When deploying containers in a cloud environment like a Kubernetes cluster, you'll want to be sure it has enough resources to operate. In Chapter 15, you'll learn how to assign CPU and memory resources to a container running in Kubernetes and how to configure memory for the JVM by applying the Java memory calculator provided by cloud-native build packs. For now, we'll rely on the default resource configuration. So far, you have created a deployment for a Spring Boot application and run it in your local Kubernetes cluster. But it's not possible to use it yet, since it's isolated inside the cluster. In the next section, you'll learn how to expose your application to the outside world and how to use the service discovery and load balancing functionality provided by Kubernetes.